So welcome back all. So it's a great privilege to have Ghanshyam, Dr. Ghanshyam Pilania as our MateriAlZ speaker. Ghanshyam got his PhD from University of Connecticut under Rampi Ramprasad, and then, as we just discussed, did a simultaneous postdoc with the Humboldt Fellowship at Max Planck in Germany and at Los Alamos. And then after that, he got converted into a staff scientist position. That's right, Ghanshyam, at Los Alamos. And some of you may recognize his name already. He's done a lot of great work in computational material science and at the interface of materials informatics and computational material science. So with that, Ghanshyam, the floor is yours. And the format is going to be any questions, unless or until you violated the laws of conservation of energy. We'll wait for the questions to be after the talk. So audience, please write your questions into the chat box and Ghanshyam will answer it after this seminar. With that, yeah, Ghanshyam.
Yeah, thanks for the introduction, Krishna, and thanks for the invitation. Today I'm going to be talking about some of our recent work on novel scintillator design and discovery, combining experiment, simulations, and machine learning. And a particular emphasis of this talk would be on highlighting materials informatics-based challenges that we came across during the course of this project. So without further ado, let me just jump into the talk. For those who are not familiar with scintillators, scintillators are simply defined as materials that convert high energy radiation to sharp pulses of photons, usually lying within visible or near visible range of the spectrum. So it's looks very simple, radiation in, light out. But when you take a closer look at the scintillation mechanism, find out that it's a very complex multi-step process. It starts with radiation interacting with the material that results in a collision cascade, formation of a lot of hot charge carriers, electrons and holes. These then multiply via impact ionization and quickly settle down to valence and conduction band edges as a part of thermalization process, and then eventually transported to an activator site, on their way getting trapped to various defect sites. Activators are typically lanthanide ions, which are doped in very small concentrations in host material, and these create 4F and 5T levels in the band gap, and these levels act as a localization site for these charge carriers. So where the charge carriers come and recombine radiatively, giving out of light, which can be collected in a photomultiplier tube and sent to detector and so on. So as you can see, it's a multi-step complex process. It involves aspects of thermodynamics, kinetics, charge transport, defects, dielectric screening. And so first principles based treatment of all the complexity at all required time and length scales is formidable today, even with most powerful computers that we have. And why do we care about scintillators? Because they form a critical component of number of devices and detectors in range of different applications. Some of the applications are highlighted on this slide. And all of these applications can be broadly categorized into spectroscopy or imaging based applications. And different applications have slightly different demand in terms of scintillator performance metrics. But for example, spectroscopy applications may require more light output, while imaging applications may put slightly more emphasis on speed. On the other hand, today scintillators are not really optimized for a given applications. In fact, it's customary to take whatever is available off the shelf. And so there is an opportunity in terms of custom scintillator design and development for a given application. So that was our motivation at the outset. Now, when you talk about scintillator design, it's instructive to look at scintillator property portfolio. And here is an incomplete list of perhaps the most important properties that we care about. The two most important properties are high light yield and fast response. So how many photons you can get out per incident MeV of radiation, and how quickly you can collect these photons outside. And typical time scales are of the order of 10 nanoseconds for most of the scintillators. In addition to that, we also, of course, the material has to face high energy radiation all the time. So we require stability under radiation. Emission wavelength need to be tuned to a specific application or detector system. High density and effective atomic number is also required for efficient absorption of radiation. And certain features of electronic structure, such as favorable placement of 4F and 5D level of these activators with respect to the band edges, or minimal presence of these deleterious defects or trap states is also required. Now, all of these properties need to be optimized simultaneously in one material. So scintillator design is a very complex multi-objective optimization problem in a target chemical space. And traditionally, it has been addressed using mainly using chemical intuition and trial and error based approaches. In few past decades, first principles calculations have added significantly, and the goal of this project was that can we use machine learning to even further expedite scintillator development. Now, when I talk about machine learning, let's first take a look at what are the challenges we face for machine learning in material science. And when we talk about machine learning in physical sciences, it's slightly different from machine learning that has been pursued conventionally in data-rich settings, for example, because here we deal with small data sets. If you, for example, if you look at Google or Facebook or Amazon data sets, they are of the order of billions. On the other hand, here in material science, if you're not looking at specific problems like potential fitting or image recognition, things like that, you are typically operating in data scarce settings, and high quality relevant data either from experiments or first principles simulations is usually very, very limited. And in such situation, it becomes extremely important to not only make predictions, but also quantify your confidence in those predictions. And so uncertainty quantification is important and critical. In addition to that, data can be highly biased and heterogeneous because now, all the data points in a particular data set need not be independent and identically distributed. They can be highly clustered in chemical space. Results from failed experiments are rarely reported. Most of the experiments are driven by chemical intuition and individual tastes and preferences. Moreover, data can come from varying fidelity sources. So one can imagine that range of computational methods vastly varying in terms of computational accuracy and cost. And you can generate data on one property from all these computational methods, and that would have different level of noise and uncertainty in that. And it may not be obvious how to combine this entire information to make optimal predictions. Experience of, so oftentimes we also know a great deal about the physics of the problem in terms of mechanistic details, fundamental laws, boundary conditions, symmetry operation, and so on. And so this information, when integrated in a machine learning model, can really benefit a lot towards a particular problem. But what should be the best way to integrate this type of information in a given situation may not always be obvious. Right, so that's also another challenge, and we have seen that recently physics-informed neural network have been very popular in this direction. In addition, our own experience and experience of others have shown that materials design and discovery problems using machine learning work best when they go hand in hand with experiments in an active learning adaptive design framework. However, in some situations, feedback from experiments can be extremely slow. And And so in such situation, one need to figure out how to break that bottleneck, how to resort to alternative um, strategies to generate experimental data in a high throughput manner. Lastly, it may not always be possible to independently optimize all properties that we care about in one single material. Some of the properties can actually have conflicting relationships uh, or inverse trend with respect to each other. A classic example is high K dielectric constant, where the energy stored in a dielectric material is proportional to the dielectric constant and square of the breakdown strength, but these two properties turn out to be inversely correlated. So one cannot really talk in terms of one single material, the best material, but you always end up with a set of material that provide you best trade-off with all possible properties, and the problem becomes how to push the Pareto optimal front, or how to get best materials in a Pareto optimal set. So these are the challenges, and during the course of these projects, we encountered almost all of these challenges in some form or the other. And so we are going to come back towards the end of this talk and going to revisit each of these. So let me get started on the how we started. So naively, one can think of on the right side, I have a property portfolio. These are all the properties I care about scintillators. On the left, I have descriptors or fingerprints or attributes of materials. And so these are my material representations. These can be composition, configurations, or features of electronic structures as shown here. And then problem is to use machine learning and integrate all the possible physics of the problem and develop a nonlinear mapping algorithm that allows you to go from materials to properties. And this works reasonably well for the training. So we did that, and the problem comes when you start making predictions, because such a model will by design, it's always trained on scintillators, and it makes good predictions for scintillators. But when you are making predictions on unknown chemistries, you don't really know whether a given compound is going to be scintillator or not at the outset. And so when you use such a model, it will spit out something, but in case of non-scintillators, that those numbers are going to be meaningless. And in fact, vast majority of the new compounds are going to be non-scintillators. This type of approach is not going to work. In another word, one need to first, these models of performance cannot be applied directly to large chemical spaces. One need to first address a scintillator versus non-scintillator classification problem, and only after when we have separated all the scintillators from non-scintillators, these models of performance can be applied to scintillators. And so that was an early lesson learned. And so then one says that why don't we just collect all the data on scintillators and non-scintillators and try to just develop a classification model brute force. And turns out that in that case, you don't really get a good accuracy, because the amount of required data to make a general model that is able to separate chemistry, a scintillator and non-scintillator chemistry, regardless of crystal structure or composition, requires much more data than we have today. And so again you fail, and so then we took a step back and basically started thinking about what is the critical feature. So let's say we have a stable material. What's the feature of electronic structure that really makes a scintillator scintillator? And so it turns out that at least for lanthanide doped inorganic scintillator chemistries, one can safely argue that its position of activator level with respect to band edges that does the trick. So if 4F and 5D levels, either of the 4F or 5D levels are buried in the band edges, then there is no scintillation because you can't localize electrons or holes there. If they are too far off deep in the band gap, then again, there is no scintillation because you need increasingly large number of phonon modes to dissipate that extra energy before you can start localizing charge carriers there. Of course, in this case, one can use chemical doping or strain to either bring the conduction band down or lift the valence band up to do band edge engineering. But ideally, you would like to have a configuration where 4F and 5D levels are in the band gap near the band edges. So the next question is then, what governs position of these 4F and 5D levels? And if you look in the literature, seems like there are two spectroscopic parameters, the U and D parameters that dictate position of 4F and 5D levels in lanthanides, lanthanide dopants. Here, the U parameter should not be confused with the Hubbard U parameter that is frequently invoked in DFT plus U calculation. In fact, this is a local property of a 4F lanthanide shell, and it represents local electron-electron repulsion in the 4F shell only. And this is well known in scintillator community. And then so once you have the position of, once you have U and D parameters, you can actually predict 4F and 5D levels within the band gap reasonably accurately. And you just need a DFT calculation for the host band gap. And you can start making predictions for scintillator and non-scintillator. So now let's take a look at these a closer look at these U and D parameters, what they actually mean and how they allow us to calculate these 4F and 5D levels. So starting with U parameter, as I said, this is a local property of the 4F shell, and it represents electron-electron repulsion in the 4F shell. So plotted here is a 4F binding energy of lanthanide ions in trivalent and divalent length charge states for the entire series of lanthanide ions with respect to the vacuum level. And going from trivalent charge state to a divalent charge state, you are essentially adding one more electron in the F shell, and that results in increased electron-electron repulsion. So the vertical distance between these two curves, the red and blue, represents the local electron-electron repulsion in the 4F shell, and that's the U parameter, and it's huge for the ions in vacuum, 18 eV or so. But when you go from vacuum to aqueous solution to lanthanide metals, due to the dielectric screening of the medium, this interaction is effectively screened, and these two curves come close together as they move up. And there is a systematic relationship between how much they move up versus how much they come close together. And this relationship has actually been quantified in Peter Dorenbos' chemical shift model. And so if we know the U parameter for any host material, we can actually pinpoint where the 4F level of a given lanthanide ion in a given charge state is going to lie using that empirical model. Now, situation with the 5D level is a little bit more complex. Here, moving from vacuum to a host environment A, these 5D levels not only go up, but they also split. And the relative shift of the lowest 5D level going from vacuum to a compound A relative to the 4F level is represented by these D parameter or spectroscopic redshift. And so once we know the U and D parameters combined with Peter Dorenbos' chemical shift model and DFT-based electronic structure for just the host of band gap, we can actually pretty reliably predict these 4F and 5D levels. So that's the take-home message. So there is slight problem here that determination of these U and D parameters requires synthesis of single crystal, followed by very accurate spectroscopic measurements and expert analysis. And this can take months just for one chemistry. And so our goal was that can we use machine learning to predict these U and D parameters, completely bypassing this synthesis and measurement step and start making predictions. And for that, you need accurate data. So when you look in the literature, it turns out that there is There is a lot of data, but turns out that good curated data sets are not there. We were lucky to find these two papers where Peter Dorenbos, who is leading authority on scintillators, has actually analyzed and curated several decades of what data and compiled in these two papers. So we use that expert curated data set as our ground truth. And then for features, we just take very simple attributes of atomic constituents of these chemistries. For example, electronegativity, ionization potential, electron affinity, ionic radii, atomic polarization, petty force, Mendeleev number, and so on. Wherever you see a subscript AV, average, that means that the quantity is averaged over all the atomic constituents. Wherever there is a minus or plus, that means the average is only restricted over either anionic species or cationic species. We also found that it was absolutely essential to include band gap, because in retrospect, we know that the dielectric screening is very important. So ideally, you would want to have dielectric constant, which is much more computationally expensive, but dielectric constant and band gap have inverse relationship. And so just using PBE band gap as a proxy for dielectric screening works well here. So with this data, with this feature set, the first thing we did was to look for pairwise feature correlation to see if there is any redundant information in our training set. So here is a pairwise feature correlation plot for those 20 features that I showed on the previous slide for the U data set and D data set. The blue means it's a positive correlation, red means it's a negative correlation, and fraction of the filled pie chart represent the strength of the correlation. And so when you take a look at this, you see that there are lots of features that are strongly correlated. And so we wanted to get rid of that redundant information. We do it in following manner. So if two features are correlated more than 85%, then we just include one of them, the one that is strongly correlated with the target property. And if a feature has a Pearson correlation coefficient of less than 25%, with the target property, then we don't include that feature, because we say that there is a not strong correlation with the target property. So we played around with these cutoffs, and eventually we found that these cutoffs work really well. When we apply this, in each case, we are left with 5 top features for the U as well as for the D data set. And when you go and plot scatter plots of these top 2 features in each case for the U and D parameters, you see that there are strong linear correlations of our top 2 features in each case. And so these are going to be really good features. Just by looking at it, one can tell that. For the machine learning model, we use kernel ridge regression. I'll not have time to go into all the details of kernel ridge regression, but very briefly, there are 3 terms of kernel ridge regression. So let's start with regression. Most simplest form of regression, linear regression. And here, prediction is represented as a linear combination of our features. It's a d-dimensional vector, so that we have d number of features, and betas are our model parameters. So that's what we are looking for. And so this is essentially a least square fit problem. You determine these these parameters by simply minimizing the least square error, summed over all the training points in the training data set, and this is it's analytical. So you can solve for beta, and so we all know about this. The problem with this linear regression is that if there are outliers in the model, and even though we are not really after outliers, we are after the average trend in the data set. The model will quickly get biased and thrown off the average trend in the data, and the outliers will have strong say. And in this case, you will find that some of the betas will be significantly large than others, and we don't really want that. So that's why we go to ridge regression instead of linear regression, we go to linear ridge regression, and by ridge, this is we mean is basically adding this extra term here. This is also known as regularization term. And what this term essentially does is it keeps all of the betas about the same size and small. So it doesn't, so no particular beta I is able to shoot, and because of that, we still recover the average trend in the data set. And then from going from linear ridge regression to kernel ridge regression, basically we are mapping our linear space onto a kernel space, which is a non-linear space. In this particular case, we are using Gaussian kernel, and this allows us to build non-linearity in the problem. And there is another hyperparameter here, which is kernel length. And so one basically need to optimize for both regularization and hyperparameter. But this is essentially kernel ridge regression in nutshell. So we use kernel ridge regression and all the top 5 features, and starting with the U parameter model here, we start building models, right? We've taken one feature at a time, taken 2 of the top 5 feature at a time, and taking 3 and so on. And the last one is where we take all the 5 features in the model. And plotted here is our performance on training and test sets for each. In each case, we take different training test splits. So we run model different times, every time randomly selecting training and test splits, and the plotted are the average performance over all these randomly selected training test splits, and error bars are the standard deviations. You see that the best performance is when all the 5 features are included here. But the best model with just the 2 features is not actually that bad. We on our test set performance is actually comparable to the test set performance of our best model. So we are not really gaining anything by adding these extra 3 features. And so in the spirit that simplest models are always better generalizable, we go forward with the simplest and most accurate model. The same story prevails in case of the D data set. Again, here the best model with the 2-dimensional feature set is actually turned out to be as good as the one with all the 5 features included. And so we go forward with that. Here again, we know that D parameter also depends on crystal field, and none of these features include crystal field description. And so we include that information posteriorly in an implicit manner. We don't exactly calculate the relaxed geometry, but we just include some classification metrics, and that alone allows us to bump up the performance by 10% on test set. And so with these models, then we compare performance. So in these parity plots, x-axis is the experimentally measured U and D parameters. Y-axis is our machine learning predictions on training and test sets. And in each case, we here shown are 5 different machine learning runs with randomly selected training and test set splits with different colors. In each case, we use 90% of the training data as training data and 10% as test set. And you see that there is a comparable performance on both training and test sets. That means we are not really overfitting. And predictions also don't change drastically by small fluctuations in the training data set. That means our model is robust against small fluctuations in the training data. So this is an example of physics-informed machine learning, because we are trying to solve a classification problem ultimately, right? We want to make predictions whether a given chemistry is going to be scintillator or non-scintillator, but we are doing so by training 2 different regression models, and the choice of those regression model is completely determined by the underlying physics of the problem. And so this is in this respect that I call this physics-informed machine learning. And maybe that I mean, that's the best we can do right now with the given size of the data set. Maybe as and when more data becomes available, these models can be improved. But this is already very powerful because it allows us to come up with an alternative scheme, completely bypassing experiments and go and start making predictions on scintillators. But the question is this level of accuracy is predictive enough? And so for that, we go ahead and start doing tests. First test we do is, can we predict chemical trends? So we take an example of double perovskite oxides. These are, so on A site, we have calcium, strontium, and barium and 50-50 combinations. On B site, we have hafnium and zirconium and their 50-50 combination. And these are very similar type of chemistries, right? So you would expect, if your model is able to capture chemical trends accurately, you would expect very similar predictions for the 4F and 5T levels. So here in this plot, all these band gaps were calculated using hybrid DFT, and 4F and 5T levels were predicted using the machine learning model. And you see that the predictions are very similar for each of these chemistries, but when you zoom in, you see that there are also systematic trends relative to one another. And these trends are in agreement with what is seen in experiments. So the next test we did was, can we predict known scintillators? And for that, we use an example of alpazolite halides. So alpazolites are double perovskite halides, and we restrain ourselves to this particular chemical space because a number of known scintillators are known to reside in this chemical space. And so we wanted to check if our scheme is able to highlight those candidates or not. So again, the band gaps were calculated using hybrid DFT, and 4F and 5D levels in each case were predicted using our machine learning model. Two things jump out from this plot. First one is that in each case, in each anion chemistry group, all the 4F levels are aligned more or less. And this is expected from physics. This is seen in experiments. This was not explicitly put in our machine learning model. This just comes out as a consequence of the fact that we are learning U parameters very accurately. And so if you learn U parameters, you will actually recover this behavior. Second thing is that fluorides and iodides are not expected to be good scintillators because of two completely different reasons. In case of fluorides, the gap between VBM and 4F levels is very large, and so one will have trouble localizing holes. On the other hand, iodide 4F 5T levels are buried in the conduction band for iodides, and so one will not be able to localize electrons there. So our best bets are chloride and bromide according to predictions, and this is actually true. Most of the known scintillators, vast majority of known scintillators in this chemical space happen to be chlorides and bromide. And so we can start, we can go ahead and make predictions, and turns out that we recover most of the known scintillators, and we also make some new predictions. Of course, these case, we haven't really tested the stability and other properties, and but these are potential scintillator candidates that come out as a part of the screening. So I'll come back to these predictions towards the end of my talk. But this is very encouraging because now we have built a scheme, machine learning based scheme, and tested it, and it seems promising. At least we can start making predictions. Of course, we don't claim to be 100% accurate every time because the models are imperfect, noise is in the data, and so false positive and false negatives are expected. But definitely we can do much better than randomly predicting or just by using domain knowledge to predict for scintillators. So as a next step, we then go and apply this developed framework to different classes of compounds. So we have applied it to perovskite oxides, garnets, and alpazolites. And in each of these cases, we have made new predictions, and these compounds are at different stages of development and optimization. And so in the remainder of the talk, I would like to give you a flavor of what we have done in each case. And so let's start with perovskite oxides. So we consider all single and double perovskite oxides. And if you consider the entire periodic table, AA prime, BP prime, O6 type chemistries, then there are more than 5.5 million compounds. So you can enumerate it in a combinatorial manner. Of course, all of these compounds are not going to be physically meaningful. If you take into account charge neutrality and geometric constraints such as A cation should always be greater than B cation for a stable perovskite crystal structure. These chemical compatibility constraint further allow us to down select from 5.2 to nearly 1 million compounds. And for these 1 million compounds, then we go ahead and start building machine learning models for stability and formability, band gap, and 4F and 5D level prediction in the band gap to make predictions of potential scintillators. So I'll not have time to go into all the details, but very quickly for the stability and formability predictions, we start with a data set of DFT calculations. We generate a data set of 3,500 compounds from first principles, while using a consistent set of parameters that is compatible with MateriAlZ project data set, so we can calculate the thermodynamic stability in a global fashion in terms of energy above hull. By using whatever has already been calculated and known experimentally, and that has been tabulated in MateriAlZ project database, energy database, and then use that data to build machine learning models that allow us to classify a new chemistry as a stable perovskite versus non-perovskite. And here are some details. So here we use a random forest machine learning model. An advantage of that model is that it also allows us to calculate relative importance of different features. And we see that the tolerance factor and octahedral factors that have been traditionally used to address the stability of these and formability of perovskites also jump out as important features. Performance of our machine learning model is in terms of accuracy is 94%, while if you just use octahedral and tolerance factor, you get somewhere around 85% or less. There are some more details about our machine learning classification model in form of ROC curve and precision recall curve, which is alternative way of representing ROC curve. Essentially, this tells us that how much better we are doing in terms of predictions than just predicting randomly. So if you look at the center panel, the red dashed line here shows a random guess. So if you label everything as non-perovskite, of course your false positive rate will be 0, but your true positive rate will also be 0. If you label everything as perovskite, then of course your true positive rate will be 100%, but false positive rate will also be 100%, and everything else will be in between. But ideally, for a perfect model, you would want to be somewhere at the top left corner here, where your true positive rate is 100% and false positive rate is 0. We are not exactly there, but we are quite close to the top left corner. And so that was just based on DFT calculations, but then we again go ahead and collect data on 1,500 perovskite and non-perovskite chemistries, which have been experimentally synthesized, and label them, and then build another classification model and with the same type of analysis, and that allows us to predict how much potential a chemistry has to be synthesized in a perovskite crystal structure experimentally. And we combine these two models to make our final predictions to predict new stable perovskite chemistries. And other details of this study can be found in this paper. I'll not have time to go into all the details. But exciting thing is that after we publish this paper, some of these predictions that we made in the paper have actually been validated by others. So I noticed this paper came out last year, and these chemistries that they have synthesized have actually been predicted in our paper that was published earlier. So that's kind of an independent validation. But our goal is not just predicting new perovskites, but we also want to go ahead and predict scintillators. And because of that, we want to make sure that we want to screen for insulating compounds, because all the scintillators are going to be insulating. If you just try to build a regression model to predict band gaps, it turns out that that model can be heavily biased by metals, because more than 90% of the chemistries are usually metals. And so before going to build a regression model for band gap prediction, we first separate the wide band gap and small band gap materials. So everything below 0.5 eV DFT band gap and metals are separated, and we only consider for our regression model compounds with band gap was greater than 0.5 DFT PB band gaps. The cutoff of 0.5 is arbitrary. In principle, you can actually use any cutoff, but we want to be a little bit conservative. And there is a high probability that any compound that has PB band gap of 0.5 is not going to be a good scintillator, at least in man-doped with lanthanide ions as activators. So we do that, and then finally we make predictions for 1,200 compounds, but we also have a cutoff of how much confidence we have in those predictions in our model, and we tighten that confidence to 90%. And as we tighten that, the number of predictions we get for the wide band gap materials quickly shrink. And so here we are just left with 310 compounds for which our machine learning model is very, very confident that they are stable, formable, and they have wide band gap. And here is the profile of the predicted band gaps. So we go back and actually now do these calculations for a randomly selected set of 150 or so compounds, and we see that DFT band gaps actually match very well with the predicted band gaps of our model. And then finally, we use our UD prediction model to predict 4F and 5D levels and select for potentially promising scintillator materials. These are highlighted as stars here. So we have identified 20 or so new compounds that are potentially can be potentially scintillating, and currently they are being looked at in more detail by our experimental collaborators at LNL. So let's switch gears and moving on from perovskites to garnets. In this particular case, we consider a very limited chemical space. So garnets are A3B5O12 type of compound. Here we allow for 2 A site cations and 2 B site cations, and A site can be occupied by either lutetium, yttrium, or gadolinium. And on B site, we have gallium and aluminum. And so within this limited chemical space, many of the chemistries are already known to be scintillating, so we don't really need to worry about scintillator versus non-scintillator classification. There are well-known scintillators like LUAG and YAG that fall within this chemical space. And if you go in the literature and search for all the data that has been published on single crystals, you find that there are about 30, out of these 54 unique chemistries, data is available for 30. And these are highlighted here with stars. So we built a machine learning model to predict light yield and for using this training data, and then fill in the blanks. And so here are our predictions shown in this plot. So now if you just focus on those 24 compounds that are not part of the original data, this is how the predictions look. I won't read too much into the quantitative scale because this is really a small data set, and we are not really sure about how much we can trust these numbers. But the qualitative trend should be meaningful. And so we go and take a look at these trends, and we find that the model has correctly learned as the aluminum concentration on B site increases, the light yield systematically increases, and so on. So we take our top 5 predictions, and then we recommend this for synthesis and testing. Ideally, you would want to go and synthesize single crystals and make measurements, but that turns out to be very time consuming and laborious enterprise. And so at least for the first pass, we resorted to ceramic single, instead of single crystals, we resorted to ceramic pellets. Now that has turns out that ceramic pellets have problems of their own. For example, if you use green pellets for experiments, because of poor mechanical strength, it leads to a lot of porosity and voids and cracking. And so you can't really reliably measure relative light output across pellets. If you sinter them too strongly, then there is a danger of cerium segregating to the grain boundary. Again, you can't reproduce your results. And so it took us some time to optimize these sintering conditions. And turns out that if you just use lightly sintered pellet in stage 2 sintering, you stop just before necking. That gives us enough mechanical strength. At the same time, the kinetics is not fast enough to allow cerium to segregate at the grain boundary. And we have shown that with these optimized processing conditions, one can reproduce the relative light yield across scintillator pellets that are processed in one batch in single furnace or across different furnaces in different batches. And you get the same answer for the same chemistry. And so once we do that, we use this approach consistently, and that this shortens our feedback time by an order of magnitude regarding reduces our feedback time by an order of magnitude. So now we go back and synthesize these chemistries and form these single pellets. So these are our controls. So we use 5 compounds in our training set. These are four, and then that are selected randomly. And then 5th one is the compound that has highest light yield in our training data set. So that's the highest light yield known in that chemical space in garnets. And then we make we do these measurements for our predictions, and we see that actually our predictions don't do quite well as compared to what is the state of the art. In fact, one of the compound actually had higher light yield, although the quantitative predictions the quantitative trend in the prediction is not obeyed, and we don't really expect it to be the case. But generally, all of our predicted compounds have high light yield, and so that was very pleasing. So in light of this, these encouraging results, we go back and actually revise our model with just in-house data, just using light yield on ceramic pellets. And then we again analyze chemical trends to see if there is anything new that jumps out. Seems like again, more or less we get the same picture. All the trends are intact except slight readjustments. So we see that as on the B, for a fixed A site, as the aluminum concentration on the B site increases, light yield increases. For a fixed B site, as the yttrium content increases, light yield decreases. And then all the predictions that came out as our top predictions in the previous round still remain in top candidates here. So in terms of whatever needs to be new that needs to be discovered in this data set looks like has already come out in the first iteration, but this establishes that we can actually use ceramic pellets as a good proxy for at least for the screening in garnets and possibly in other type of chemistries. And this is much faster as compared to just using single crystals. And our best candidate, the Y2 Luag that came out as high light yield compound in the ceramic pellets has since then has been synthesized as a single crystal. It still looks very promising and currently being developed for mission relevant applications. So last but not least, We have also made some predictions for alpasolites, and these 3 predictions were synthesized, all of 3 when show luminescence in under UV, but when you do radioluminescence experiments, only one of them shows very strong luminescence and other 2 don't. So we are currently in the process of figuring out what's going on. Most likely it has to do with trap states and defects in the material, but this is work in progress. And this is in collaboration with Maria Zurarleva's group, and with Daniel Strom, who is a graduate student who is actually doing these experiments. And this is work in progress. So with that, we have come full circle. So let's revisit our challenges, and reflecting back on the challenges that we discussed in the beginning of this talk. In this project, we had to deal with, again, small data sets. So uncertainty quantification was always performed using bootstrapping. We made sure that we always selected simplest possible models for better generalizability, and all our features were selected in such a way that they ensured causal relationships with the target property, the U and D. Again, if you just go in the literature and try to train machine learning model on the entire everything that is out there, you don't really get any good predictive models. In this particular case, we used a very exclusive data set by Peter Dorenbos that was published in those 2 review papers, and then all our DFT calculations were consistently performed with the same set of parameters. We didn't really mix data on single crystals and ceramic pellets, and so those were some of the things that we took care in terms of biased and heterogeneous data. Domain knowledge integration turned out to be a key thing here. We developed 2 regression models to solve a classification problem, and the nature of these 2 regression models was completely decided by the underlying physics of the problem. Iterative feedbacks from experiments in terms of for single crystals turned out to be extremely slow, so we had to resort to ceramic pellets, and we established that ceramic pellets can actually be used as an effective proxy for single crystals during sintering stages before we move on to the actual single crystal synthesis. And then the 2 most important properties, the light yield and decay time, turned out to be inversely correlated. So brighter scintillators are slow, and the fastest scintillators are dim. And so there is, again, no best scintillator here, but again, turns out that we can always trade little bit light output for speed by playing around with activator concentration and co-doping. So with that, I would like to go ahead and conclude. So in this talk, I've shown you a domain knowledge informed machine learning approach to expedite scintillator design and discovery. We discussed challenges that are unique to this data-enabled approach, and we presented a physics-informed scintillator versus non-scintillator classification model, which after combined with models of performance applied to different crystal structures, perovskites, garnets, alpasolites, and each of them we have identified new chemistries which are at different stages of development and testing. And then finally, we have developed a hierarchical down selection approach for large perovskite chemical space, including both single and double perovskites, where we have developed models for stability, formability, band gap predictions, and these models have implications beyond scintillators. They can be used to address many different problems, and so we are currently working on putting together a data in brief paper and a GitHub repository where we are going to share all the data with the community so that others who are working on similar problems can be benefited with that data if possible. So with that, the work performed during the course of this project has been published in a number of manuscripts, and And some of them are listed here. Some of them are currently in progress and coming out soon, will be coming out soon. With that, this was really a team effort, and many researchers actually contributed to the work. So acknowledgements are due to the entire team. This work was funded by Lenel LDRD, and computational support was provided by Lenel high performance clusters. With that, thank you for your attention, and I'm happy to take any questions.
Thanks, Ghanshyam. So the floor is open to the audience to ask questions. So let me start off by, I mean, is there a fundamental reason, Ghanshyam, that there is an inverse correlation between light and speed, or I mean, whatever?
Yes. So it's related to oscillator strength, right?
Okay.
So yeah, so the 4F and 5D level, the gap increases, then the oscillator strength. So so the transition becomes faster. But then the energy of the light that will come out is proportional to the band gap, and so as your so you'll get less light but faster.
Okay, but is there some chemical intuition on how we can then tune this so that we can have both? I mean, that would be an excellent forward problem that machine learning can solve, right?
Exactly. Yeah. So so this is I mean, I think to address this problem, like it's not universal, within given chemistry, I think that's the case. But if you are changing chemistry, going to different chemistries, that you will of course be able to deviate from that trend. That said, usually these, I mean, so there are radiative and non-radiative recombination pathways, right? And but what you can only get light output from radiative, and there are always non-radiative pathways. And so the strategies that target increasing light yield, they basically try to inhibit non-radiative pathways. Mm-hmm. And that can be done by bringing down the conduction band so that your main trap states are actually, they get buried in the conduction band edge. And so those trap states will not be able to contribute to the non-radiative recombination pathways, and as a result of which you will get that energy through the radiative channel. And so those kind of strategies are there. But the thing is, I mean, accurate quantification of electronic structure and exactly pinpointing how, where these levels are, what is their relative order, has been a challenge in realistic materials. Ideally, when you go to higher level, more accurate, beyond DFT calculations, many body calculations, you don't really consider all these self-trapped excitons or defects. You have very simple models of not really have like grain boundaries or extended defects, and
absolutely.
Those are not important. Yeah.
Cool. I think there's one question from Anirudh. Anirudh, if you want to ask the question.
Hi, I was just wondering, how do we generate more descriptors for property prediction or for classification problems? Because often I've seen there are very few features or properties available for any problem that we choose.
Right. It highly depends on what kind of problem you are trying to solve and how much data you have. If you have a lot of data, then you can actually start generating lots of fingerprints. There are there are standard packages. Of course, you can take advantage of that, but it depends on the problem, what kind of fingerprints you want to include. For example, if you are looking at perovskite chemical space, different types of chemistries spanned over the entire periodic table, then you want to ensure that your fingerprints have notions of chemical similarity, right? If you are just focusing on predicting energies in a molecular dynamics run on a fixed chemistry, then you worry more about configuration. That what are the local configurations being sampled by your dynamics, right? And so that said, there are these codes that are available. For example, MetMiner is a good example. If you are interested in chemical problems, those molecules, there is a package called RDKit, which is open source, and there are descriptor modules in there. You can also use your domain knowledge and try to understand the mechanistic details of the problem, and then try to come up with your own fingerprints or descriptors that you can then go and compute from first principles or a lower level of theory. So yeah, these are all the possible scenarios to consider.
Okay, thank you.
So before others interject, let me ask, I mean, you touched upon strain engineering of band gap. I mean, that's well known, but is that an option for you to, as an extra, knob to get the best performance?
I mean, depends on application again. So if you just want to have a detector that will just detect radiation in case there is some event once in a while, then maybe you can have like very fine, very sophisticated material. But most of these scintillator materials have to work in rough and tough conditions, and in those cases you are always better off with like bulk single crystal oxide refractory type materials, which are very robust against defect formation and all that. So
okay.
Hi, very nice work, Ghanshyam. I have a question regarding the machine learning methods. And so I'm just wondering, have you benchmarked with other machine learning methods such as XGBoost or random forest? Because especially XGBoost, it's just a package, almost always XGBoost outperforms random forest. So I'm just thinking about just a few minutes, it can improve the performance of your model.
Yeah. So the thing is, so that's what, like, there are these transparency complexity trade-offs here across. So when you look at explainable machine learning is a big topic these days, and when you look across and compare different machine learning models, as you increase complexity of a machine learning model, right, its predictive performance should also go up, given that you have sufficient data to train on. That said, XGBoost is essentially, it's you have random forest, and on top of that, it basically starts iterative fitting, where in each iteration it fine tunes the weights, takes the residue, and then tries to adjust the weight so that the residue. So it goes through these iterative cycles, right? And oftentimes you can get better performance, but there is a very strong danger of overfitting. So at least that has been my experience, that XGBoost almost always tries to overfit. And on the other hand, advantage of random forest is that it is extremely difficult to overfit a random forest model because it's intrinsically robust towards overfitting. And there are like, different papers about that. But it's so bagging and boosting, right? So it's bagging type approach, whereas in boosting it's easy to overfit. Whereas random forest is when you are training a random forest models, you not only take different subsets of features, and you also take different subsets of your training samples, and then you basically start generating random trees, and that lead to a random forest, and then you make predictions by ensemble averaging over all of these models, right? And so it's extremely difficult to overfit, even if you. So there are two hyperparameters in random forest, right? Number of trees and the tree depth. And so as you increase number of trees and tree depth, the performance increases at certain point, but after that it just becomes flat. Even if you include more number of trees or more increase the depth, it doesn't really keep improving. It just gets flat. And so even if you have a very if you overestimate these two hyperparameters, you are safe against overfitting.
Gotcha. Yeah, I understand your concern. Yeah, that in terms of interpretability, I would say these two tree-based methods, they are comparable. They're on the same level. I would suggest maybe control regularization in XGBoost. That will help with the overfitting. But again, random forest, it's a bit, maybe a few years before XGBoost, and XGBoost with regularization, it always outperform random forest.
That's true. Yeah.
Sorry, Ghanshyam, any other questions, folks, from the audience?
I have a question. Yes, good morning, everyone. I came in a little late today. Nice to see you all. Ghanshyam, welcome. My question is more I'm an experimentalist, so I'm interested, what are people doing to increase the databases that are available for your work, right? You probably, need to be well aware where the data is coming from so you can, continue to expand your work. What are some of the highlights you think around the country or that are developing the data sets?
So what are the highlights that developing? So I mean,
so is Leno has a team on high throughput material synthesis, and is there efforts across the country to speed up the data generation?
So of course, there are well-established data repository like MateriAlZ project database, OQMD, Jarvis, MateriAlZ data facility, and MateriAlZ computational materials repository. Then in Europe there is NOMAD, Novel Materials Discovery, and so they have taken they have integrated all the data. So these are well-known repositories, and they have been there are dedicated teams and groups have been working on these. So that said, in terms of addressing individual problems, I think people have been generating their own data set, because usually you want, as I said, these are very application specific, and oftentimes you have your own vision and you have your own ideas. So for that, obviously you always want to generate your own data, but you can benefit it from what is already documented there. There are also journals that publish these scientific data sets, like Scientific Data is one of them. Data in Brief is another one. And so it's
and are these individual data sets complete enough for the machine learning work?
So
is there enough standard across the data sets?
So I would say it's a work in progress. Right now, there are efforts that are being led to kind of systematize, fair concept of material science. So fair data sharing principles, which is essentially that you want to streamline and encourage the data reusability and data findability and interoperability, and so there is something called common materials data format that people have been working on, and so if you are using a code, oftentimes databases are tied to a particular code like WASP or Quantum Espresso, Abinit, and so can we come up with with parsers that basically take that data and put it in a common format that can be used across codes. So basically platform agnostic. It just and so those kind of efforts are currently in progress, and papers are out on those. Yeah.
Thank you. Thank you. I think that's very important.
I think so. Yeah.
So Ghanshyam, another maybe a random question, but what if those papers weren't available where you could look up all the values, properties?
So now I think every journal requires authors to address that data availability issue, right? So it's a mandate now that you if you are not sharing data, then you basically give justification of why you are not providing the data, or if you are sharing, then you are supposed to provide like a GitHub repository or data is available from authors upon reasonable request or some statement like that. And so if it's not there anywhere, then I think it's perfectly fine to just write to the author and request for the data. I think that's the last resort, but in most of the cases, I think, yeah, people share their data unless it's a work in progress and they are worried about getting scooped up.
Actually, sorry, I misspoke. What if that Journal of Luminescence data wasn't available? How would you have solved this problem? Like, where would you have looked up all the parameters?
Yeah, so that's the beauty of data sharing, right? That it enables others to do things that you would not have thought otherwise.
Yeah.
So
okay.
Yeah, probably we could have gotten stuck or had to resort to like computational approaches only. Will not be able to train directly on experimental data.
Yeah, so something for highly correlated electrons, that's DFT plus.
Exactly. DFT plus DMFT or something like that.
Sorry, Ankit had a question. Sorry, Ankit.
Yeah, no problem. So I'm just going to actually extend Bruno's and Krishna's question on this. So I have two questions actually. The first one is, what do you do when you have the data which is a sparse set? That means you have missing gaps, missing data sets, missing data in the entire data set. And clearly the effectiveness of the prediction methodology using machine learning relies on how dense you have the data set. And so if it is sparse, are there any efforts to still sort of work with that? And my other question is, how transferable are these machine learning frameworks when, say, you want to design materials to screen materials for applications like catalysis, where, again, the same physics may apply?
Yeah. So regarding sparsity, it again depends on where the sparsity is, if it's in the feature space side or it's in the property space. Let's say you are interested in multiple properties and some of the properties are missing. Now the question is, what's the cost of acquiring new data points? Is it simple? It's just a matter of just doing DFT calculations and updating the data set. Then, that's where we should start. If you want to prioritize that, what gap should I be filling first, because the cost of generating data is so high, you don't want to go and do all the experiments, then maybe you can start with adaptive design framework or active learning, where you start with your most complete data set and then predict and based on those predictions you prioritize your where you want to basically. So basically kind of balancing the trade-offs between exploration and exploitation. And then last thing is there are also something called multitask learners. So that can really help because usually traditionally, at least in material science, what people do is that they have one target property, train a machine learning model, then they have a second target property, train another machine learning model. But turns out that sometimes these properties have correlation with each other. And so if you are training a multitask learner that that can take advantage of these inter-property correlations, that gives much higher prediction performance. And so these are some of the things you can do. In terms of transferability, I mean, specific to our case, we have addressed stability, formability, band gap. And so these are just regular descriptors, right? You know, if a band gap is important criteria, then the model applies, as simple as that. We have also shown that, you know, 4F and 5T levels in lanthanides can be predicted. Maybe similar framework can also be predicted for transition metal, like D levels. You know, you have D site dopants. And Arun Kumar, Manodi Kanakitori, who was graduate student after me in Ramprasad group, he is a faculty at Purdue now. He has done a lot of work in that area. So learning these defect levels using machine learning model with Maria Chan's group. He did that. So those are some of the things.
All right. Thank you for a great talk.
Yeah. Thanks, Ghanshyam. And this was a great talk. Very, very useful, very timely too. I think the material science and engineering really needs, you know, to start using more and more materials informatics, more interfacing between, you know, data, diverse data sets, all that stuff. I mean, that to me is the, if not the next frontier, a very important next step in pushing the field of material science. So thanks a lot. I'm sure we'll have more opportunities to discuss and look at collaborative opportunities too. Meanwhile, thanks a lot for all the audience. I mean, all you guys have been very patient sitting through. Usually people log off as soon as they're done with the 50 minutes. So thanks a lot to those folks too. And Ghanshyam, please reach out. I think there are going to be lots of collaborative opportunities between UFA, ASU, Lano. So let's keep that discussion going. And one final, Bruno is our fellow co-organizer too. He threatened not to attend today, but somehow he got back. So hi, Bruno.
Hi, I'm always trying my best. We all are. We are very excited to be here every Friday. But Ghanshyam, you're not too far away, so don't be a stranger. We're not too far from each other, so.
Cool. So with that,
nice to meet you, Bruno. And yeah, thanks again for the invitation.
Oh, thanks, Ghanshyam. So yeah, let's keep in touch. And bye, Ankit. Bye, Bruno. Bye, all.
Bye, everyone. Bye.